Okay, so welcome everyone to this week's seminar. We're very happy to have Bao Wang. So Bao is an assistant professor at Utah. He did his PhD from Michigan State University, and after that went to UCLA to work with Andrea Petosian and Stanley Osher, where he won the Chancellor's Award for Postdoc Research in 2020. So we're very happy to have him speak this week. And he is talking about advances momentum in optimization, algorithm, and neural architecture design. So Bao, please start.
Okay. Thanks, Matt, and thanks everyone for coming to my talk today. And today I will be talking about the advances of momentum in optimization algorithm and neural architecture design. And so first, just my general philosophy of the deep learning. Maybe I should say deep learning is approximately contains two major parts. One is the big data acquisition, and the second is designing high capacity deep neural networks. And the third part is how to optimize this, the parameters of the network. The last part, maybe also one of the most important parts, is high performance computing. Okay. Well, from the mathematical viewpoint, maybe designing deep neural networks and improve SGD algorithm is more interesting than connecting big data and designing the chips for high performance computing. Okay, so I will be focusing on talking about neural network design and improving SGD algorithms. So first, deep learning in the past more than 1 decade, it has achieved a lot of very remarkable success in both revolution in technology and also the science. In technology, like do the face recognition, autonomous driving, machine translation, and also play this AlphaGo. And many of them has been commercialized, where AlphaGo is in some sense is still at like the infant stage. It's not very mature yet. Many people might think it's still kind of hype. Well, in science, it has also been used to solve many very different scientific problems, like the protein structure prediction. I think it was around 2.5 years ago. There was a computation called CASP. It's basically to predict the protein structure, the 3D structure from the sequencing information. It has been lasted for many, many years. Well, 2.5 years ago, when deep learning was successful applied to this field, then things get changed completely. I would say it's a revolutionary work. And also in drug discovery, people to find these molecular structures and to check the properties of the potential drugs using deep learning approach. Also in material design, it has achieved really a lot of success. Well. On the downside of deep learning, it's quite expensive. Like the designing neural network architectures, like it's very expensive. It's mostly art instead of science. Usually people will not say I based on some first principle to design a neural network. It's very different from classical physical models. Classical physical models typically start from some principle and then derive the model and then design numerical method to solve that and analyze the asymptotic behaviors and so on and so forth. Well, designing deep neural network is mostly architecture search or like a lot of trial and error. Also, training deep neural networks is very expensive. There is no principal approach in selecting optimization algorithms. There are a lot. I think there are around 10 very popular optimization algorithms, like SGD with momentum, ADAM, ADGRAD, and so on and so forth. Also, the training deep neural network, the convergence usually is very slow. In particular, if you look at today, the state-of-the-art deep learning model for natural language processing, for machine translation, a single training from the scratch, it can cost millions of dollars. It's very expensive. So then our principle is simple. We design simple and principled approach converge with the working machine learning algorithms. Today, I will talk about 3 examples. One is let's solve accelerated SGD with restart. Second is integrating momentum into recurrent neural networks. The last part is heavy bond neural ODs. Okay. So first, I will be talking about the schedule restart momentum for accelerated SGD. Now we go to the technical part. If you have any questions, feel free to stop me. So let's just look at typically a training a machine learning model, y equal to gxw. W is the parameter of the model. X is your input data, y is your prediction. This can be formulated as the empirical risk minimization problem. Suppose I give you a training data xi, yi, I from 1 to capital N. N is usually very big, and G is a very complicated machine learning model, like say deep neural networks. L is the loss function. For instance, for classification, L is the cross entropy loss or the log likelihood. And for regression, this can be taken simply as the mean squared error. This problem, it's mathematically it looks like the form is very concise, but it's a very challenging problem since first the parameter lies in a very high dimensional space, can be like up to billions. Okay, and also this n can be very big. For image classification, n sometimes like millions or a few hundred millions. For machine translation, this n can be much bigger. And also F is highly non-convex because the model G itself is very non-convex. So these three challenges makes the problem very difficult in practice. Then for such difficult problem, typically people will prefer to choose a very simple algorithm, like say first order gradient descent. Let's recap some properties of the gradient descent. If F is a smooth function, that means the gradient of F is Lipschitz. Then start from an initial point W0, we run gradient descent by doing the following iteration, Wk equal to Wk minus 1 minus S times gradient F Wk minus 1. It's like the steepest descent algorithm. Locally, every step I try to do the best. Then for this simple algorithm, in different settings, it has different convergence rate. For strong and convex case, if we choose the step size appropriately, we can show that Wk converges to the optimal with the rate L divided mu. This is the linear with the rate L divided by mu. This is the condition number of the problem. And if F is convex, then we choose the step size 1 over L. We can show that the objective value converges with the rate 1 over K. Here, we measure the objective value because for convex case, W might go to infinity. For instance, 1 over X, if we want to minimize this function, when X is greater than or equal to 0, then eventually the optimal value should be infinite. That's why we measure the objective value. If F is non-convex, then we measure the gradient of F, just converge to a stationary point. This stationary point can be local minimum, local maximum, or saddle point. We'll just convert to the stationary point has a convergence rate square root of 1 over K. So like the rate become worse and worse as the problem become more and more challenging. So let's look at one example. This is a very challenging problem because this problem has one eigenvalue 0, and the solution space lies is the same as one of the eigenspace. So this is a challenging problem, and in particular, we consider also high dimensional problem, 1,000 dimensional space. It's a quadratic, but convex, but not non-convex. Then we run gradient descent. Let's look at the convergence. Fxk minus fx star. Like after we run like 50,000 iteration, the error is still like 10 to minus 3. And if we want to get to machine precision, like 10 to minus 14, then I think you will wait for maybe several days in order to finish this single run. It's a gradient descent is very slow. Then to improve this, we can use the last of momentum or look ahead of momentum. Here, this one is equivalent to the standard heavy ball momentum, but Wk instead of evaluate the gradient as Wk minus 1, we should evaluate it like approximate Wk. Then this momentum, it converges faster than the standard gradient descent, but still far from satisfactory. Again, if we want to get a machine precision, it will take really a lot of time. So the convergence rate is still 1 over K. Okay. Then alternatively, we can just use the heavy ball momentum. In practice, using heavy ball momentum and look ahead momentum performs similar, and the convergence rate is still 1 over K. Then why momentum works? Usually, one interpretation was because in high dimensional problem, typically the condition number is very big. If you run gradient descent, the trajectory will be highly oscillatory, and then it goes to the minimum very, very slowly. And with the momentum, you essentially can smooth the trajectory with the with one-step extrapolation. You can smooth the trajectory, and then it converges to the local minimum much faster. The takeaway is that momentum smooths the trajectory and significantly speeds up gradient descent. Now, a very significant work here is called less sort of accelerated gradient descent. On top of the previous look ahead momentum, we simply replace the constant momentum with an iteration-dependent momentum, like k-1 divided by k+2. This one was already simplified. The original Lestrov methods, it took a much more complicated form of this coefficients. Okay. And this one, you can show that this convergence rate is 1 over k squared, and it oscillates. It's not a monotonic method. So some comments about the Lestrov accelerated gradient. It's one of the most beautiful and mysterious results in optimization. And it's not a descent method because you look at the trajectory, the object value trajectory, it contains a lot of rips and bumps. So to show the convergence rate from the continuous viewpoint, it turns out to be extremely simple. You just construct an energy function, also called a Lyapunov function, and you take the gradient of this energy, this Lyapunov function. It's a monotonic decay. Then this function converges with rate 1 over t squared. But in discrete case, I similarly construct some other discrete and Lyapunov function, we can show the convergence rate. So as we said, this sort of accelerated gradient is not a descent method. It contains a lot of rips and bumps like to here. Then you will run a lot of steps, like a few hundred steps, just goes up instead of goes down. Then it's natural to ask, can we further accelerate that sort of accelerated gradient? Because it's not a monotonic method. Okay. So yes, we can, in each step, we can observe the function value. So here the idea is to do restart. Okay. Originally, we do k-1 divided by k+2. Then we can measure the function value. If the function value increases, the FWK is bigger than FWK-1, then we reset this MK to 1. Otherwise, we just let it increase. And then in this case, numerically, you can see that this purple curve was the Lestrov accelerated gradient, where this red one is Lestrov accelerated gradient with restart. This is called adaptive restart. Function restart according to the function value adaptively. And if we enforce some actual condition called sharpness, sharpness is something close to strong convex, but weaker than strong convex. And then in this case, we can show the geometric convergence rate. Actually, this is consistent with the experiments. You see this one converge almost linearly. Another restart is a schedule restart, because in the previous adaptive restart, you always need to measure the function value. To measure the function value for simple function, that's cheap. But for a neural network, this can be very expensive. So then instead of doing adaptive restart, we set some landmarks. We divide the whole iteration interval into several sub-intervals. And in each interval, we restart the momentum after Fi iterations. Fi iterations, then basically just mathematics can be formulated as this. And then this yellow curve is the schedule restart. Again, it converges like linearly. And we can prove this geometric convergence with the sharpness assumption in the previous slide. Now, all the previous results are about gradient descent. We have access to the exact gradient, but in practice, usually we don't have access to the exact gradient. We only have, in training neural network, we only have the mini batch gradient, stochastic gradient. Okay. Then in this case, we want to ask, can Lestrov accelerate still accelerate convergence of stochastic gradient descent? The answer is no. We go back to this example. And instead of using the exact gradient LW minus E1, we corrupt this gradient with a Gaussian noise. But this Gaussian noise is not a very intense. This Gaussian noise has a decay variance. The variance decays during the iteration. And then we run the algorithm. We see that the original gradient descent is this black curve, and gradient descent with the momentum is this blue curve. We said, well, that sort of acceleration, this trajectory become much more oscillatory, and also much slower than the gradient descent with constant momentum. And adaptive restart looks similar to the gradient descent, because you can think about this. Since the gradient has some noise, then each step the function value might change the sign. Then essentially the momentum becomes 0 in every step. Then this degenerates to the gradient descent. Well, schedule restart converges even faster than the adaptive restart. Then we consider another case. If this Gaussian noise is stronger, more intense with constant variance, let's still compare all these algorithms. We see that that sort of acceleration becomes much worse. Okay. The error accumulates and does not converge at all, but all the other methods still converges. Okay. The last example I want to show is the real SG stochastic gradient descent. We train a logistic regression model, and we see that that sort of accelerated gradient with stochastic gradient descent. Then this purple curve, look at this, the error accumulates linearly. So here the key message is that sort of accelerated gradient still accumulates error, and the schedule restart performs the best. Then we can prove an upper bound of that sort of accelerated gradient descent with stochastic gradient. The upper bound is of order k. Is just the FWK minus FW size of order k. It's different from the gradient descent case. For this, if we have access to the gradient, then it should be 1 over k squared. But now, using stochastic gradient, it's of order k. But we cannot prove a lower bound yet. So then two comments about the adaptive restart and the schedule restart. Adaptive restart, it restarts too often. It basically degenerates to the gradient descent without momentum. Where schedule restart, with the appropriate restart scheduling, it can lead to an optimal trade-off between convergence and error accumulation. Then we propose the following algorithm called a schedule restart Sgd. It's different from the schedule restart Gd. We're using a mini batch stochastic gradient instead of using a gradient descent. And also we restart the momentum term periodically. Well, not periodically, just according to a schedule. Set some landmark Fi, and then after there, we restart the momentum. Schedule restart resets the lateral momentum according to a fixed schedule when stochastic gradient is used. Then, by doing this simple schedule restart, we can show the convergence of the algorithm. So far, the convergence rate is the same as the standard Sgd, but in practice, it performs better. Let's say first we use schedule restart Sgd to train a neural network for CIFAR 10 and CIFAR 100 classification. Then you see that in each stage we converge faster than the Sgd with momentum. Here Sgd is Sgd with momentum. Meanwhile, another nice thing is schedule restart. It's not a monotonic method. When you restart less often, it will accumulate error again. Then it can sometimes, based on our empirical observation, it can bypass some local minima and get to better generalization. As also we trained the ImageNet, the performance is similar. And then we compare, as we said, sometimes it can bypass some local minima that's not generalized very well. So then we compare this generalization performance for CIFAR 10, CIFAR 100, and ImageNet. We train residual network with 110 layer up to 1000 layer for CIFAR classification. As you can see that as the network gets deeper, the margin becomes wider, consistently for CIFAR 10 and CIFAR 100, and also for ImageNet. For ImageNet, we train 50 layer residual network and up to 200 layer residual network. Again, this the performance is consistently better. So the improvement of Sgd over schedule restart Sgd over Sgd continues to grow with depth. Since RSGD oscillates, it can escape better minima and avoid overfitting in very deep networks. Overfitting, if you look at the training image net with a 200-layer network, this 200-layer, I think, already contain 68 million parameters. It's a very big model, but then it's already overfit in some sense. Then we look at also, because it converges faster, then we can reduce the number of training epochs and compare the performance. So here we train schedule restart Sgd with 100 epochs only, whereas Sgd with momentum using 200 epochs. Again, even in this case, we save the computational cost by half, but we still win. Well, then is the lesser of acceleration like optimal? Theoretically, yes, because we can construct some counterexample to show the convergence rate. The best one is 1 over k squared. But empirically, usually we can do better. Here we just use the nonlinear conjugate gradient method. Then we can see that it converges even faster, also almost monotonically to the local minimum than the lesser of acceleration with even with restart. So here, well, we cannot prove the theoretical guarantee yet, but empirically it performs much better. The second part, I want to talk about designing recurrent neural networks with momentum. Look at a recurrent neural network. It's basically described mainly by this dynamical system. HT is sigma UHT minus 1 plus W times XT. Here, XT is the input sequence X1 up to X capital T. And then we encode XT into the hidden state HT with the parameter W. But HT, meanwhile, it need to contain the previous hidden state information and weighted by this weight matrix U. And for the recurrent neural network, we also have the universal approximation theorem. So it basically says a recurrent neural network with enough capacity can approximate any dynamical system with arbitrary accuracy. It's different from the universal approximation theorem of the multi-layer perception. Multi-layer perception is approximate any function, but now recurrent neural network is to approximate any dynamical system. And then using this, we can design this recurrent cell. And a recurrent neural network is a concatenation of multiple recurrent cells. Then recurrent neural network has multiple applications, mainly for sequence modeling. Like sequence to label in this, there are also two scenarios. One is each HN encodes HXI and the previous information. Another one is, and finally use HT to get the output. Another scenario is average of all these hidden states to get the prediction. One particular application is text classification. Suppose I give you a lot of articles. I want you to classify these articles based on the topic, like the sports, entertainment, finance, and so on. We want to classify these text articles instead of the image. Well, we can also do the image captioning using this sequence to label recurrent neural network. Another application is sequence to sequence and synchronized. Input a sequence, output another sequence. One particular application is a part of speech tagging. There's also asynchronized sequence to sequence modeling. Input a sequence X1 to X capital T, and then we get the hidden state H up to H1 to up to H capital T. And then we extrapolate these hidden states, HT plus 1 up to HT plus M, and we get the prediction Y1 to YM. So this one, essentially HT plus 1 already contains all the previous information. Then this can be used to do the machine translation because it's already captured the semantic information. So to train the recurrent neural network, because this recurrent neural network shares the parameter U and W, then to train this, a popular algorithm is called a backprop through time. Suppose we have the input sequence X1 to XT, and the output is Y1 to YT. We consider this sequence to sequence modeling. Okay. And the loss will be X1, Y1, there is a loss. X2, Y2, there is another loss. And up to XT, YT, we sum all this loss. Then we compute just one term. partial LT, partial U. By chain rule, we will get, it looks like a sum k from 1 to t, partial HT, partial U, times partial LT, partial HT, and times this product. The major difficulty comes from this product. Each term is dk times U transpose, where dk is a diagonal matrix, and the diagonal entry is the sigma prime. Sigma typically is the sigmoid or the hyperbolic tangent function. So this the diagonal entries are strictly less than 1. Strictly less than 1. Then let's look into this value, this product. If the spectral norm of dku transpose is bigger than 1, then this value increases exponentially. So this will converge to infinite very rapidly. Well, for this case, if the gradient is too big, then there are some simple ways to deal with this, like gradient clipping, or recognize the spectral norm of U transpose. Recognize the spectral norm of U transpose. Then dk, because dk usually is small. Then if U transpose is also small, then this value, the spectral norm of dk U transpose will be small. So this case is called the exploding gradient. But exploding gradient can be resolved easily. The major challenge is the vanishing gradient. If dk U transpose is less than 1, then this product will go to infinite very, very quickly. So then this is a major obstacle to learn the long-term dependency, because k from 1 to t, this gradient is almost 0. You cannot really establish a connection from let's say hk to hk plus t if t is big. You cannot learn such a dependency. So one solution is the long-short-term memory. It's a very famous model. It replaces the original recurrent neural network with a very complicated dynamical system. This contains more parameters, this significant more parameters, and also using the gating mechanism. So after very complicated computations, we can see that in this case, the gradient partial hk plus 1 over partial hk is dk. It does not depend on U anymore. Well, empirically, it achieves much better performance than the recurrent neural network. So another mathematically more interesting approach is to enforce U to be a unitary matrix. When we train this recurrent neural network, we want U to be unitary. And this can be numerically efficient solved by using the exponential parameterization and using some D group, some properties of the D group. Well, our solution is to integrate momentum into the recurrent neural network. So let's revisit the recurrent cell. If we do a simple change of variables, we can simplify HT to HT equal to phi HT minus 1 plus UT. If we informally treat UT as the gradient, and then we add momentum into this update, then what we get is we will have PT equal to mu times PT minus 1 minus SUT, HT equal to phi HT minus 1 minus PT. So this is the momentum cell we proposed. By doing a reparameterization, VT equal to minus UPT, then we get the following cell. Graphically, it can be visualized in the following. The left-hand side is the recurrent cell. The right-hand side is our model. Compared to the LSTM, our model has almost the same number of parameters as the recurrent cell, because U and W are typically contains the most number of parameters. We just have 2 more hyperparameters, mu and S. But this usually we choose S to 1 and tune the mu a bit. Let's look at why this one is better. Again, we revisit this backpropagation through time. For the backpropagation through time, partial L, partial T, for the standard recurrent neural network, then this has this term, the product K from T to T minus 1, dku transpose. But for our model, we have the product of dku transpose plus mu times sigma K. And this mu sigma K, sigma, the diagonals of sigma are all greater than 1, because it's the gradient of sigma inverse. So then this will not vanishing. So for the LSTM, it basically designing LSTM can remove this term U, but we are even better. Not only remove U, but by adding some bigger term to avoid vanishing. And then we visualize this partial HT, partial HK plus 1 over partial HK. We visualize this during the training. As you can see that for the standard recurrent neural network, it's vanishing very quickly. After, like, look at the y-axis. Right? From the last step, this is training for the MNIST classification, pixel by pixel MNIST. That's usually it can capture only around 100 steps dependency. But for our model, momentum recurrent neural network, it's almost a level vanishing, except converge to almost the steady state. So here we measure the L2 norm of the hidden state. And we can also design other momentum recurrent neural network by different parameterization. We can get different architectures. Okay. Also, we can use in other algorithms like the ADAM, it becomes even more complicated than the momentum recurrent neural network. But the number of parameters are still the same. Just the dynamics become more difficult, more complicated. So here the message is that the momentum can also be integrated into LSTM and other recurrent neural network more easily. So we compare the empirical performance. So here, first we consider pixel by pixel image classification, MNIST classification. Here, instead of input an image using a convolution filter to get the features, we first just flat the image into a sequence of length 784 because it's 28 by 28. So then we train using different recurrent neural network. We have the momentum LSTM, ADAM LSTM, IMS LSTM, Schedule Restart LSTM, and the original LSTM. We see that, interestingly, we know that the optimization algorithm itself converges faster. But here we use the same optimization algorithm, but just a different recurrent neural networks. We see that it also converges significantly faster for the MNIST classification. Next, we consider different data modality. We consider the speech data set. This is a benchmark called timid. So again, our model not only converges faster, but also you look at the test loss, we are significantly slower. We are significantly smaller. So finally, the last example, benchmark example we consider is the water level pantry bank. We converge, this is for the next water prediction. Again, we converge faster and generalize better. This our model is better than the benchmark models across different data modalities with image, speech, and language modeling. Also, our momentum-based model achieve better accuracy than the baseline LSTMs. Then look at the accuracy for the MNIST classification. We consistently weak. And for the timid, our improvement is much more significant. Look at the original LSTM. This test MSE like up to around 10. So far the best result around 10. Then we almost halved them, get to 5 something. And for the pantry bank, perplexity, we also win. Meanwhile, our method can also be integrated into the orthogonal. Orthogonal is just the approach. We enforce U to be a unitary matrix by using the D group parameterization. Then in this, the model, using D group parameterization, they call the model D-trip. And then we put our momentum into the D-trip. We, again, outperform the D-trip significantly. And in this case, we, again, revisit the permuted MNIST and the timid. In this case, the timid, we achieved a really remarkable result. We get the test accuracy up to 1. Originally, we see that the LSTM is like 10, and then we use momentum LSTM, we get 5, and then further integrate with this orthogonal parameterization, we get MSE is 1. It reduced by 10-fold. Okay. Then finally, we evaluate the computational efficiency. We see that our model, to achieve certain level of accuracy, compared to the LSTM, we're using only less than 1/3 of the computational time. So we are not only better in terms of accuracy, And also we are computationally more efficient. The last part, I will talk about the continuous time model, heavy bond neural OD. Okay. Neural OD is mathematically can be written as this: dHt dt is f ht t theta. Well, usually f is something you don't know. Give you a sequence of observed data. I don't know what this data follows some equations. Then I simply parameterize the right-hand side with a neural network. With a neural network, for instance, I can do a two-layer network, sigma W2 sigma W1 H. This is the neural OD. And to solve this to train this neural OD to get this parameter theta, usually we use the adjoint method. This, I think, if people in the inverse community, this adjoint method is a standard method in the inverse problem community. Then this dl d theta, we do to evaluate this gradient, just the integral from t0 to t at partial f partial theta dt, and at satisfies this equation. And to solve this equation, usually we use the numerical solvers. The number of iteration needed is called the number of function evaluations. It's a continuous analog of the depth of the model. Since one iteration, you need some certain number of floating point operations. And if you need a more number of function evaluations, then just evaluate multiple times. The bottleneck of this model is NFE can be very high, and this neural OD can fail to learn long-term dependency. If I give you a sequence which is extremely long, then maybe you just learn something locally, but you cannot learn this global information. So then again, previously we talked about the gradient descent with momentum, in particular the heavy ball momentum. If we take the continuum limit with the appropriate scaling, here the scaling is the square root s, then we can derive this heavy ball OD. It's a second order OD with a damping term. Essentially, it models the damped oscillator with an appropriate damping term. Then what we did was we try to parameterize this right-hand side f minus gradient f with a neural network, and we call this heavy ball neural OD. And the heavy ball neural OD is equivalent to, if we denote dH dt as mt, then it can be written as the first order OD system. So one nice property of the heavy ball OD is it's in some sense self-adjoint. The adjoint of this heavy ball OD is d square at double prime at plus minus gamma dat equal to the right-hand side is another function. Because the adjoint method, you solve from capital T to 0, solve this backward in time. And therefore, we do a change of variable. Then we can rewrite this heavy ball OD into the original, its adjoint state into the original in the forward time equation. This again is a heavy ball OD with exactly the same damping parameter. Then it's because heavy ball method usually converge to the stationary point much faster. Then it's natural for us to motivate that this not only forward propagation faster, but also backward solve the adjoint state equation can be faster also. Another one is we look at this adjoint state. For neural OD, we derive this adjoint as partial L partial HT is partial L partial H capital T times the exponential of this. Because this is exponential of the right-hand term, the integral T capital T to small t, partial F partial H. This term can be very big. If this integral is very big, out of control, then this partial L partial HT go to 0 very quickly. But for our model, we can show that its adjoint state satisfies this equation. The integral, this is exponential of the integral of another matrix. This matrix has some very nice property. This M is suppose originally this partial F partial H is n by n. Now M will be 2n by 2n, so it contains 2n eigenvalues. These 2n eigenvalues are not arbitrary, but instead we can pair them into n pairs, and each pair has a constant sum. The sum will be t minus capital T gamma. So in this case, the eigenvalue, usually we can do some regularization to make this eigenvalue not too big. In this case, the eigenvalue will not be too small either, because otherwise the sum will not be this constant. Also, we can tune the value of gamma to modulate the eigenvalues. Then the adjoint state of the heavy bond ULD will not vanish. So first we can numerically compare the number of function evaluations. We look at we compare with 3 benchmark models: the original ULD and the augmented ULD and the second order ULD. Our model differs from second order ULD in that we're using a damping term. But heavy bond second order ULD, there is no damping term. It's very important. It's crucial. Okay. Then we see that for the standard ULD, the forward propagation is acceptable. But you look at the backward solve the adjoint equation. It's extremely expensive. In particular, when we want the numerical accuracy to be high, it can take like up to 700 or mostly failed actually. And for the augmented ULD, it's similar. Perform similar to the ULD. Second order ULD is better, but still is hundreds of number of function evaluations. It's equivalent to like the network is hundreds of layers. If you look at our model, then we consistently better, and also the forward and the backward are like linearly with each other. This is about the function evaluation. Last example I want to show is the work-to-do kinematic simulation. It's a benchmark example in the reinforcement learning. So here we just want to learn this system, learn this time series. Then we benchmark with the number ULD and augmented ULD. Then we see that for ULD and augmented ULD, then this problem very poorly. Not only the number of function evaluation as the training goes, the number of function evaluation forward and backward both increase almost linearly. But our model, there is just a sharp transition. After that, the number of function evaluation is like a constant. And then regarding on the testing, we are also much faster. The number of function evaluations determines the speed of the inference. Also, the training loss, we are much smaller, and the test loss, we are also much smaller. So as a summary, today I talked about 3 things. The first part is the schedule restart sgd acceleration. The second part is using momentum to improve recurrent neural network. The last part is heavy bond ULD. For the schedule restart sgd acceleration, it can accelerate convergence. Meanwhile, it can improve the generalization. Second, momentum recurrent neural network, it can mitigate the vanishing gradient issue, and it can speed up training and improve the performance of the trained recurrent neural network. For the heavy bond ULD, it can reduce the number of function evaluation and accelerate training, and also it can learn the long-term dependence.